Hi, good morning. I'm Shuo-Yen from National Cheng Kung University in Taiwan. And first, I'd like to thank the organizers for the invitation. So today I'll talk about our work in adiabaticity engineering in guided wave optics. And this work is the result of our collaboration with Professor Hong's group at National Sun Yat-sen University, also in Taiwan, who helped us with the fabrication and the characterization of a lot of these devices. So this is a brief outline of my talk today. Because we're talking about adiabaticity engineering, so naturally the devices we consider here are adiabatic devices, which relies on mode evolution to operate. So first we'll talk a little bit about the differences between mode coupling and mode evolution based devices in guide wave optics. Then, in order to engineer the device adiabaticity, we need to define a metric for device adiabaticity. So we'll show you how we calculate that parameter. Then this adiabaticity engineering approach falls within a larger set of protocols used to accelerate system evolution in quantum mechanics, called shortcuts to adiabaticity, STA, which have also have many applications in optics. So we'll briefly walk you through that. Then I'll talk about how to engineer device adiabaticity through the device geometry. And I'll show you some device examples. Finally, I'll conclude my talk. I'll show you the most common mode coupling based devices, which is the directional coupler, and where two waveguides with fixed width and spacing are brought closely together. So we probably all know that by engineering the device spacing and coupling length, and we can couple light from one waveguide to the other with the desired ratio. And these DCs can be made very compact, but the main problem here is that if we look at the couple mode equations, the parameters, the coupling coefficient and the waveguide mismatch are very sensitive to the input wavelength and the device geometry, which is highly affected by the fabrication technology. So these devices naturally have a narrow bandwidth and a very tight fabrication tolerance. So then I'll show you a few examples of mode evolution based devices. So the first one here is the tapered fiber to a tapered waveguide coupler. So to show you how this device works, and if we look at the side view of this coupler, so you can see a tapered fiber on top and a tapered waveguide on the bottom. And the goal is to couple the input fiber mode efficiently into the waveguide mode. And if we solve for the super mode along different positions of this coupling or mode evolution region, and if we pay closer attention to super mode 1, and we can see that at the beginning of the evolution region, the super mode 1 is very close to the fiber mode. And as the super mode 1 evolves along the evolution region, and you can see that it gradually evolves to the waveguide mode. So if we can make sure that the input light evolves along the single super mode, then we can have very efficient coupling from the input fiber to the waveguide. And the key here is to avoid coupling of the super mode into the other super mode. And another common adiabatic device is the adiabatic 3 dB coupler. Again, we have two couplers in proximity, but different from the directional couplers we showed earlier. The device geometry, which is the width here, changes along the mode evolution region. And at the beginning of the mode evolution region here, we solve for the super modes, and we see that one of the super modes is very close to one of the input modes. And the other super mode is very similar to the input light from port 2. So if light can evolve along one of these super modes, and we can see that because at the end of the evolution region, if we set the width of these two waveguides to be the same, and again, we solve for the super modes, and we can see that we get asymmetric and asymmetric super modes, and which corresponds to perfect 50-50 splitting between these two waveguides. So if the input light can evolve along one of these super modes, then we can have very good 3 dB coupling. And the key here, again, is to avoid the coupling between the super modes. And the advantage of these mode evolution-based devices is that because their operation is based on the mode evolution instead of mode coupling, so they are very robust against fabrication errors and wavelength changes. So they are naturally very broadband. So as we can see that these devices are robust, but the problem is that in order to satisfy the so-called adiabatic condition or adiabatic criterion, the devices are typically very long. So how do we solve this problem? And before we go out to solve this problem, we have to first define device adiabaticity. So I mean, it's all written here, and here's a adiabatic condition in optical waveguide. You can find that in the reference here. And if we look at this equation closely, and that means if this so-called adiabatic condition is satisfied, that means the coupling between modes N and M here is very small, and which is what we wanted in adiabatic evolution. So if we look at the numerator, it tells us the strength of coupling between these two super modes due to the variation of the mode profile itself. So if the device geometry changes too fast, then the numerator will be large. And if we look at the denominator, it tells us if the propagation constants of these modes are very different, then we will have a large denominator, and which reduces the unwanted coupling. So this pretty much gives us an idea of how we look at this adiabaticity parameter, which tells us how much the unwanted coupling is. So with this definition, we then go to really calculate this parameter in guided wave devices. So when we started working on this problem a while ago, 2017, we kind of just waved our hands and drew analogy between the orthonormal condition in quantum mechanics and optical waveguides. Then we just said that and came up with this following definition for adiabaticity parameter for optical waveguides using the vectorial modes in the optical waveguides. And we've been using this definition to engineer the adiabatic devices with very good success. But turns out what we did was not exactly very precise. A more precise definition can be obtained from local couple mode theory, and the adiabatic parameter for optical waveguides can be defined as the terms in this box. So basically, if we know the the electrical and magnetic field for the guided supermodes, and we know its variation along the propagation direction, then we can calculate its adiabaticity parameter along the evolution path. And this term basically gives an upper bound on the unwanted coupling from mode N to M. So, but fortunately, this definition is only different from our previous definition by a factor of 4. So as you'll see in our later derivations or designs, we are only concerned about the relative value of this parameter rather than its precise value, its absolute value. So the design ended up being the same. So we go back and look at the adiabaticity parameter again. And from the definition, we want it to be much less than 1. And we also know that because this rate of change of one of the optical modes is highly dependent on device geometry. So which means if we know the adiabaticity of a particular device, then we should be able to redistribute its adiabaticity parameter or design the distribution of this parameter through your geometry design and to optimize it. So this is my favorite slides in this talk because you have beers. So before we go into the details of adiabaticity engineering, we briefly just go back to the so-called shortcut to adiabaticity protocols. So we can consider we are transporting a glass of beer. If we do it very fast, then this is similar to the so-called mode coupling. So you get your beer quickly, and it's cold, but you might end up with only half a glass of beer, which is very depressing. And this mode evolution process can be seen as a robust process to transport this glass, but it takes a longer time. So you end up with a warm cup of beer, which I really hate. And this shortcut to adiabaticity protocols are ways to obtain, basically just to get your beer fast and make sure it's cold. So it's always nice. But you can notice here that these STA protocols are typically a bit longer than the most efficient mode coupling protocols. So you can see it as a compromise between the conventional mode coupling and volt evolution schemes. And so let's use examples to explain how to engineer device adiabaticity. So let's go back to the 3 dB coupler we explained before. So in these conventional designs, we typically use a linear taper function to change the width of these waveguides from different width, for example, 300 nanometers and 500 nanometers to 400 nanometers each. So because we have these definitions of for adiabaticity parameter, so we can calculate its adiabaticity along the evolution direction as shown on this graph here. So how do we redesign the taper function then to redistribute this parameter then to achieve this shortcut? So we will introduce a few different protocols. So basically, we are changing one geometrical parameter to achieve these so-called STAs. So the first protocol we'll introduce is the fast quasi-adiabatic dynamics, FAQuad. which we also borrowed from quantum mechanics. So this dotted line here on the right is the original linear taper function. And with this linear taper, we have this adiabaticity distribution. And the problem here is that we see that in this linear taper designs, the device adiabaticity at this region is actually pretty small. And it's very big at the end. But using a linear taper design, you basically have to keep increasing the length of your device in order to suppress the adiabaticity parameter at the end of the device, which is not very efficient. A more efficient way is that we should vary the device parameter in the beginning of the structure where the adiabaticity is small, and then we slow down its variation at the towards the later part of the device where the adiabaticity is big. That way, we can obtain a even distribution of adiabaticity parameter, and which is way more efficient than the conventional linear distribution. So that's the idea. We basically look at the parameter, then we can increase the speed of geometry change when the parameter is small, and we then decrease the parameter change when the adiabaticity is big, and that's the concept behind this protocol. So yes, when C is big, then we slow down the variation, so we can homogenize the adiabaticity. So with that, then how do we actually calculate the Farquhar protocol? So if we go back to the definition of adiabaticity parameter again, we can use the chain rule to take out this D, which is the only device parameter in our design. And in order to obtain this term on the right, we can assume a linear taper function in the design. So for a linear taper function, this derivative of the design parameter against Z is going to be a constant. So with this being a constant, then we can obtain this value. And then with very simple math, we can obtain the desired taper function. So now we talk about some device examples. So we actually go out and design this 3 dB couplers using the Farquhar protocol we just introduced. So as you can see, this is the simulation first. So this is our obtained Farquhar taper function, so which is highly nonlinear as compared to the conventional linear taper. And as you can see, it's very efficient. We can actually get very efficient mode evolution in 11.6 microns, and which is typically more than 70 microns if we use a linear taper design. So these are some of the devices we fabricated, and we also chose different taper length. And these different colors shows the device performance at different temperatures. So as we can see, these devices are very robust and against temperature. And as the device gets longer, and you actually get better flatter and flatter spectrum, close to 50-50 splitting, which is also similar to conventional adiabatic devices, but this is much more efficient. And as we compare it with the common 3 dB couplers, for example, the devices up here, MMIs, DCs, they basically rely on mode coupling. So they can be very compact, and some of them have very good bandwidth. But typically you can see the bandwidth are smaller, and these conventional adiabatic devices, as I mentioned earlier, you can achieve very good bandwidth, but the mode evolution could be longer. But in these STA protocols using Farquhar, we basically achieved a compromise between these two extremes. So we get the benefit from both worlds. So we can apply this idea to design variable ratio splitters. So in these 3 dB couplers, we have the width of the waveguide at the end to be identical. But if we slightly change them, and if we look at the output supermodes, you can see that the light distribution in these two output waveguides are changes as we set different width difference at the end of the coupling region. So you can see we can achieve different splitting ratio with different width difference. So again, we design these devices and we first go out and simulate its spectrum and fabrication tolerance. So on the top, you can see for different splitting ratios, you can see a pretty broadband response. And at the bottom, if we consider the fabrication error, which causes different variations in width, you can see these devices are pretty robust. So here again is the fabrication results. We made different devices. So you can see the measured average splitting ratio is close to the theoretical value, and they show pretty flat spectral response. And this is a slightly complicated slides. I apologize. But again, when we calculate these adiabaticity parameters, we see that they are different for different wavelengths. So if we, for example, we calculate its value at 2010 and 1310 and 1410, and you see that they look pretty close, but if you put them on top of each other, they are a little different. But what this graph tells us is that for each wavelength, there is a optimum rate of change for a device parameter. And in here, when this value is large, because if you look at R, it's dz over dw. So if this R is large, that means we should slow down the device parameter change. And if the value is small, then we should increase the rate of change. And if we put these lines on top of each other, then we can see that in different sections, we should follow the rate of change that is given by the corresponding wavelength. And then we just basically choose different sections on these overlaps. Then we can, again, optimize the adiabaticity for different wavelengths. And again, we can also do that for different polarizations. So we just apply the same idea. We calculate the optimum distribution for different polarizations, and we stack them up. And again, we come up with a optimal design for polarization independence. So again, we just use the previous technique. So this again is a very simple 3 dB coupler device. Then we only engineer the only single parameter, and we end up with pretty good polarization in independent 3 dB couplers. So this is the TE input, and this is the TM input. And the mode evolution region is only 27 microns long. And we can compare that to a conventional linear taper, which is much longer. And again, the same concept can be applied to basically most adiabatic devices. So for example, this polarization splitter rotator. In the first part, you have a taper because this waveguide has a vertical asymmetry, so you have mode hybridization. Then you can convert the input TM mode to the TE1 mode at the end of this taper. And the TE0 still stays in TE0. Then we use a asymmetric directional coupler, which is also adiabatic, to separate these two. We basically convert TE0 to TE0 here, and we convert the TE1 here to the TE0 of the top waveguide. And so we can optimize the adiabaticity in these two sections separately. So this is the adiabatically engineered taper function for the first section. And you see that the input TE mode still stays TE. The input TM mode is converted to the TE1 mode. And then in the second section, basically the TE0 stays in TE0. TE1 is converted to TE0 on the top. So on the right is the fabrication results. So we can see for the TE input, it basically goes out from the bar port and very little is coupled to the cross port. And for the TM input, you also get pretty good extinction ratio, polarization extinction ratio. And here we basically made this devices on a 8-inch wafer. And we also look at the different positions on the wafer. And you can see that across the whole 8-inch wafer, we can also see very good polarization extinction ratio. And because, as you know, you expect plus 10 or 20 nano differences across the with the waveguide thickness difference across the whole wafer. So this basically verifies that these devices could be very tolerant to fabrication errors. So again, this adiabaticity parameter thing, we only considered one design parameter previously, but actually this could be, it's a function of multiple device parameters. So in here we show that if we consider two device parameters that we can engineer, and we can rewrite it as this. And so we applied this idea to the, again, to the 3dB couplers. So instead of only changing its width, we also incorporated this device tilt or the shift of the axis, which was actually pioneered earlier by Professor Popovich's group. And so we can basically plot the adiabaticity parameter as a function of two design parameters. One is the shift here, and one is the width here. So if we look at the map, we can find a path on the map which gives you the smallest adiabaticity parameter along the evolution. And that gives us a very good design. So here's a design example using this. And I think one of my students, he gave a poster yesterday on this topic. And so we basically applied the previously introduced FiO technology, and we used the adiabaticity map, and we found the most efficient evolution path on the map. And here's our design results. And the mode evolution region is about 20 microns. And on the left, you can see the wavelength. So you have very large, almost 250 nanometers of bandwidth, and very good fabrication tolerance. This is the width variation. And if you look at the power of the super modes along the device, and you can see that this is exactly what we wanted. All the powers stays in one of the super mode, and the unwanted coupling is actually almost completely canceled. So due to time, I think I'll skip this part. So here's my conclusions. So adiabaticity parameter of optical waveguides can be engineered using one or multiple parameters. And the fastest shortcut to adiabaticity can be obtained by FiO. And we can achieve broadband and polarization independent operation by adiabaticity engineering And this technique is applicable to various devices based on mode evolution. And thank you very much.
Yes, great work. And yeah, substitute cardiac, our team are working on that. Okay. So one question, have you tried with the silicon nitride with a similar diabetic osmotic directional catheter?
Yes, great question. Yes, we've tried this with different material platforms, yes. Okay. So including silicon nitride. And I mean, everything always looks good in simulations, right? So, but we already send them out for fabrication. So hopefully we'll have some good news.
Yeah. Yeah, with our experience, we send for MPW for the, because we sweeping the splitting ratio from 1090 all the way to 5050. And yeah, it's always because we're working a little bit lower wavelengths at around 850.
Okay.
And yeah, the overall results always either the splitting ratio is weird or the center wavelength shifted a lot.
Yeah. The experience we had with this device is that typically you send up for MPWs and you have to sweep your parameters and expect them to work. But fortunately for these designs, we typically get them to work with just probably one design because they are supposed to be pretty robust. But that's on silicon where you have more or less good control of the geometry and material parameter. Yeah.
That's good. Thank you. Yeah. Thank you. And yeah, I think for our second presentation is strong. So probably we'll skip it and